today's speaker is Eric Raban, who will speak on Eisenstein Congruences and Euler systems.
Okay, thank you. So I would like to speak on some work in progress on an attempt to make an automorphic construction of Euler systems. And so I'm going to talk about maybe the simplest examples that we could consider and try to convince you that that could be generalized to other situations where we don't have the geometric object or units to construct Euler systems. So if you take n in integer and you consider theta n the primitive root nth root of unity, and you consider this element inside Q of mu n, take n greater than 1. So if n is divisible by at least 2 primes, you know that this is a unit called a cyclotomic unit. And so if you look at its image in H1 Q of mu n Zp of 1 by the Kummer map, you get a class I'm going to call Cn1. That so this system of elements in this Galois cohomology form a compatible system. Of elements satisfying the following. If you take the norm from Q of mu nl to Q of mu n of this element Cn1, then you get 1 minus Frobenius L inverse of Cn, 1 if L does not divide n, and you get Cn otherwise. And so this compatible system of elements have been used by Rubin to prove one divisibility towards the main conjecture, and then using the class number formula, he could deduce the full main conjecture. And as we know, as it has been recalled by Chris, one can prove the main conjecture also proving an opposite divisibility using Eisenstein congruences. And so Eisenstein congruences in the work of Ribet and Maser-Weitz gives the construction of elements in H1 of QP mod ZP of, let's say, M. And you can also twist by some finite order Dirichlet character chi. So here we see that we have classes which are not torsion classes, and here we have torsion classes. And so those congruences are what we can say those are horizontal congruences, which mean by horizontal, that means that we fix a weight k. So in that case, k is 1 minus m. And one look at congruences between the Eisenstein series of weight k and character chi. And we look at congruences with form f, cusp form f. So f is some power of p, and f is a cusp form of weight k, and same level. So on the other hand, so here actually the Eisenstein series in that case is ordinary. So so then we can also talk about vertical congruences. So by the work of Ida, we know that if we start from F an eigenform, let's say ordinary eigenform of weight k, or let's call it k naught, then we can construct a family, roughly speaking, Fk of cusp form, such that Fk naught is the original F, and such that, well, if k is congruent to k prime modulo p minus 1 and some I power of p, then Fk is going to be congruent to Fk prime modulo some I power of p. And the most k and k prime are close periodically. The most Fk and Fk prime are close periodically. But so this is when we start from an eigenform which is ordinary. So, and all the forms in the family are going to be ordinary forms. So if you do that when we start with this Eisenstein series, so if you take F to be the original ordinary Eisenstein series, then it's well known that what we get is a family of ordinary Eisenstein series of weight k. And this is a family that Chris presented at the end of his lecture today. So in the non-ordinary case, the result of Ida has been generalized by Coleman. So maybe I can use this. So if F is not ordinary, then we can, if A, PF doesn't vanish, then Coleman generalize Ida's result. So one way to formulate this is to consider weight space. So X is going to be a originating space such that the QP bar points are the homomorphism from ZP cross to QP bar cross. Take the continuous homomorphism. So in particular, a weight K here is seen as T gives T to the K. And so Coleman proved that if you start from F, a finite slope eigenform, then you can find, let's say, U inside the weight space X, an affinoid neighborhood of the weight K. Let's say F U, a formal Q expansion, A N Q N. Such that so A of n is going to be an analytic function, really analytic function on U, and when you evaluate so this formal Q expansion to classical weights, you get the Q expansion of the classical eigenform, at least if the weight is sufficiently large. So if we apply this to another Eisenstein series, then we get the following. So we apply this. To EK critical. So this is the eigenform defined by, you take the, so I'm going to assume that here that K is greater or equal to 4. And you take EK critical, the Q expansion is going to be the Q given by ek of q minus ek of qp, where ek is a level 1 Eisenstein series of weight k. And then in that case, you see that the Fourier coefficient of ek critical is exactly p to the k minus 1. So now the the slope is exactly k minus 1. So let's call it k naught. And so if we apply Coleman's result to this, what we get is a family fk. So k in some neighborhood u of k naught. And so fk is going to be of weight k and slope k naught minus 1. So you see that as soon as k is strictly bigger than k naught, fk cannot be Eisenstein, and therefore it is a closed form. So basically, when we start from this Eisenstein series and we apply Coleman theory, what we get is a family of eigenform which are cuspidal except for the original point. And so now if we apply the deformation theory of Galois representation, what we get, so the deformation theory of representation. So what we get basically is representation rho from GQ into GL2 of let's call it this FU. So FU is going to be the fraction field of AU. May assume that AU is an integral domain, and such that the trace of rho U, so it belongs to AU always, and trace of AU is going to be when we evaluate at the point corresponding to k naught. So what we get is 1 plus epsilon k naught minus 1. So this is a cyclotomic character. So basically, this is a family of irreducible Galois representation that becomes reducible exactly at this point. So by the construction of a suitable lattice, we see that we can construct an extension of the form QP of k naught minus 1 QP, which means that we get an element in H1 QP of k naught minus 1. So if you do that, if you take a pair k naught and chi, so distinct from 2, 1, with chi is a Dirichlet character of level n. No, I started from the case just level 1 here. So now I consider the general case where I take a level, a Dirichlet character chi of level n, and then in that case you consider the Eisenstein series E k naught chi, and I'm going to normalize it so if you look at TL acting, so it's going to be the critical Eisenstein series of weight k naught on level chi. So what you get is L to the k naught minus 1 plus chi of L chi And if you apply the UP operator, so you get pk naught minus 1. So this is for L not dividing NP. So you see that if you apply the same thing, what you get, so maybe I put a K inverse here for. So what you get, you apply the same construction. What you get is a class in H1 of Q, and then you have QP of K naught minus 1 of chi. So in particular, if you do that for K naught equals 2 and chi non-trivial Dirichlet character, you get an element in H1 Q, Q of mu n, QP of 1, with the action of Galois of Q mu n of Q given by the character chi. And so therefore this class, let's call it, let's say C 2 chi of n. So this class should be related to, the you take chi of u and well, try this way. Take sigma, sum of a sigma in Galois of Q of mu n, Q, and you put chi of sigma inverse, and take C Cn1 that I have defined at the beginning of this lecture, which is the image by the Kummer map of the cyclotomic unit twisted by sigma. Yes?
Are you going to say what properties of ramification you have of this class?
Well, no, but I can tell you. So actually, this class is going to be unramified everywhere, and that P is going to be crystalline. And so when you take K naught not equal to 2, this is automatic. And for K naught equals 2, you have to, it's obviously semi-stable, but to have the crystallinity, you use the theorem of Kissin. So you see this kind of construction, this vertical construction, gives you an element that should be closely related to the cyclotomic units. So therefore, this is natural to ask the question if we can recover the cyclotomic units using this construction. So question is, so can we cover Cn1 by this construction? So Cn1 belongs to H1 of Q of mu n, Zp of 1. So here the classes that I have constructed may have denominator, and they are not well, I mean, they are defined up to an element in QP. So the question, therefore, is can we make the previous construction integrally? And if we can, that would give another construction of an Euler system. So I'm going to explain what we can do So for that, I need to introduce a lot of notations. So I'm going to fix n an integer, equal to 1, fix k naught, and then I'm going to consider m k naught for gamma 1 of n p qp dagger, so which means this is a space of overconvergent forms of level n, well, for level gamma 1 and p, and weight k naught. And so inside, I look at the space of form which are of finite slope. And so I introduce the Echo algebra T k naught ZP. Well, T k naught n, which is the Echo algebra acting on this space.
Sorry, what's the definition? This is just the subspace.
This is a subspace of finite slope forms.
Just the topological closure of all the.
Yes, yes. So you look at the Echo algebra generated by TL, L not dividing N, and by UP. And so you have an action of lambda n. So I'm going to assume for simplicity that k naught is even here. And so lambda n is going to be ZP bracket delta n. And delta n is the group of diamond operator z over nz cross divided by plus or minus 1. So you have a natural action of lambda n on this space, and it is inside the Echo algebra. So it's going to be over ZP. So so a remark that will be useful at some point. So if we consider T prime k naught n inside T k naught n, which is going to be the principal ideal generated by UP. So in other words, every element here is a compact operator acting on this space. Then we have a map n prime into lambda n, which is a trace map. And which is lambda n linear. And basically, when you take an element T in T prime n, and you apply this trace map to T, and then you project on the chi component, then dp of chi. Then it's going to be the trace of T acting on the form of level k naught on character chi. So of course, those algebra are not finite type of ZP. But so what we can say that you can write tk naught as a projective limit of tk naught n less or equal to h, where this is the algebra acting on form of slope less or equal to h. And those are finite type. So yeah, I didn't say, but I can put powers of p in the level, of course. So it follows from Coleman's work that so for all n, there exists un. So for all n and for all h, there exists u and h, a neighborhood of k naught, such that you have a Barnard space Bu and H. Well, I mean, actually, not a Barnard space, but even a projective finite rank A of U module. Or finite rank. Such that, well, I'm going to call it like this, such that when you you take the tensor product over for some weight k inside U and H, then this is isomorphic to M K, so equal to H, 1 and P. Of course, when you vary n on H, in particular when H grows, then this neighborhood has to shrink. But we can still define this, and we can define also the corresponding equialgebra on it, Tu and H. Equal to H. It's going to be so this I look at this equialgebra as A of U and H, not delta n algebra. And the not here means that I consider analytic function, rigid analytic function on this neighborhood which are bounded by 1. So to keep the integral structure of the equialgebra. Okay, so now so you have the map of evaluation, zero evaluation at k naught. You go to ZP, and then you reduce modulo P. FP. And so you consider O hat, the localization completion of this ring at the kernel of this reduction map. And so here this is canonically isomorphic to, well, not canonically, but this is isomorphic to the Niwazawa algebra with one variable. I'm going to call it W. And so the evaluation W equals 0 is going to coincide with the evaluation at K naught here. Okay? And so the Ecker algebra now I'm going to consider, I'm going to localize at O hat. So I'm going to tensor this by O hat. So I'm going to consider T N H going to be T N N H and I'm going to consider Tn now projective limit. And so using always the same series of compact operators. So here you have an ideal prime and O hat, which is generated by UP, and then you have a map. So you can define this map at this level here already, even without taking less or equal to H, and then you extend it by linearity using this definition. So in O hat delta n. And this map is such that this prime and K naught, that you have a commutative diagram like this.
Sorry, that's a stupid question. So, I mean, when you're choosing these neighborhoods,
Yes.
there's some sort of small radius.
Yes.
Now, as you increase H, these neighborhoods shrink.
Yes.
So, I mean, you don't get canonical isomorphisms with this power series. I'm just confused about I mean, this limit over these T less than equal to H.
Yes.
I'm just worried about the compatibility of these maps in terms of these choices.
Well, I mean, if you want to just take a set of neighborhoods that are included in each other, you choose an ordering of this neighborhood, and that's it. Then you can always, so if you have a neighborhood which is included in a one, so you have a restriction map, and then you compose with localization. This is commutative. Okay, so now let's go back to the Eisenstein map. I mean, this local ring is defined without any, you don't need to choose such an isomorphism, just to make things concrete that I fix one. Okay, so so now, so we go back to the Eisenstein map. So we have a map from T K naught n into lambda n, lambda k Eisenstein, well, going to lambda k n, that then TL to L k minus 1, k naught minus 1 L inverse, and UP to P to the k naught minus 1. And you of course, you can compose. Here you go from N O hat. So now let's talk about Galois representation. So we cannot construct a Galois representation taking values in GL2T, but we can construct a pseudo-representation. So this definition has been done by Wiles. So you have a map from Galois group to Tk. Well, you can even define it directly to Tn. O hat. So you have maps which A, D, and you have a map from GQ cross GQ Tn O hat, going to sigma tau x of sigma tau. So if you have an actual Galois representation into GL2 of say f, so sigma gives A sigma, B sigma, C sigma, D sigma. So the A and the D behaves like those 2 and 3s, and the x of sigma tau is B sigma C tau. And you can make this such that A of the complex conjugation is equal to -1 to the k naught -1, which is -1 in that case, and D of C equal to 1, and okay. So in particular, if you compose this, if you compose, let's call this pseudo-representation Cn O hat, which is going to be the map A, D, X. Compose Cn O hat with lambda k naught n. So you get the pseudo-representation attached to this Eisenstein character. So therefore, what you get is A of k naught n of A sigma is going to be the cyclotomic character to the power k naught of -1. And when you do that with D of sigma, what you get is the finite order character diamond n, taking value is in delta n, which is just Galois of q of mu n plus over q. So this is just a projection on this group. And lambda k naught n was with x of sigma tau is equal to 0, because this is reducible. In fact, if you take any Galois, take any homomorphism from T into QP bar here, if you compose this pseudo-representation with this isomorphism, you're going to get something reducible only if you are at one of those Eisenstein points. So therefore, you can deduce easily that. So if you look at Pk naught n, the kernel of lambda k naught n, then this ideal is the defining ideal of the reducibility locus. Locus of psi n O hat. And so in particular, the map, well, so this is the kernel from T n O hat lambda n. In particular, the map x sigma tau takes value in pk naught n, and it generates this ideal. So what one can remark, moreover, is that if you look at this map, x from GQ cross GQ into P k naught n modulo P square n. Then actually this map, because modulo Pk naught, the equialgebra act as the Eisenstein character, you deduce that this map actually defines an element in H1 of Q lambda n of K naught minus 1. So H1 of Q lambda n of 1 minus K naught. In other words, with respect to the variable sigma on tau, x is a cocycle with respect to sigma for this character, and tau is a cocycle with respect to this character. So here the action of lambda n has to be the inverse of the action here. So here the character is the inverse of this character. So I put a minus 1 here. Okay, star here. So in fact, you can rewrite this as, well, you take omega 1 of Tn O hat with respect to lambda n and tensor lambda n. And here's so this is a Tn O hat module, and so here you tensor with respect to Tn O hat with the character lambda k naught. So we want to construct our elements in here. So you see from this construction that so I have construct elements in. Oh, sorry, I forgot to put here. Tensor. So if I can find in here a module or a quotient isomorphic to lambda n, basically I construct elements in here, tensor elements in here. So if I fix one if I fix tau, for instance, I can therefore get an element in here. So if one fixes tau, and if one can project Pn over Pn square over 3 lambda module of rank 1. So we get an element in H1 Q lambda n of k naught minus 1, which you can identify as using Shapiro's lemma at H1 Q of mu n plus Zp of k naught minus 1. And you can certainly do that. However, it's not clear that the elements that you're going to get, if you want to do that for all n, it's not clear that you're going to get a compatible family. So all the difficulty here is to get a compatible family. And so the outcome of this is that we don't really get a compatible family of elements in here, but rather a compatible system of elements in this tensor product. And I'm going to explain why. So you have a map from ρ delta n into Dn O hat, and then you have so you have this lambda k here, and so you can look at the exact sequence over n. Yeah, sorry. T O hat n over lambda n. And here you have T O hat n over ρ hat delta n. And here you have omega 1 ρ hat delta n over lambda n. Tensor T over n. And so this, because ρ hat is just Zp double bracket W, so this is just T ρ hat n dW, and okay. So I'm going to look at this exact sequence, and I tensor with lambda n with respect to lambda chi Eisenstein. So what you get is lambda n map omega T hat n so lambda n, which is the p modulo p square that I have defined before, and here I have omega 1 T hat n over ρ delta n. So lambda n. So this is a lambda n module. So from the construction I have explained before, just taking one family, one can see that this module is not a torsion module over lambda n. If you invert P, you get at least one copy of lambda n tensor QP. So now we can ask what about this module. And so one can prove the following lemma, is that if the eigenvariety if the critical Eisenstein points over weight space are étale, then well, critical Eisenstein points of weight k naught on level n, then what n tensor lambda n is torsion over lambda n. So I'm going to introduce eta n naught, the annihilator of this module. So this is inside lambda n. And you see that if you pick an element phi in here, if you multiply phi by, well, I mean, so first if we are in that case, it's because this is torsion, this map has to be injective. So in particular, in that case, lambda n, well, p over p square is injective. So now if you look at your x sigma tau, and you multiply by phi, because it kills this quotient, it should land in the image here, in this image. So this element belongs to lambda n. So therefore, what you get, because if it has a kernel, it's going to be a ZP module of rank at least 1, and that because I know that here I have at least one copy of lambda n tensor QP. If I invert P, I will not, and because I know that when I tensor with QP, this is 0. I know that this has to be of this type, so therefore it has no choice. Okay, so therefore you see that if you take element phi in eta n 0, then you construct element x phi inside H1 of Q of mu, well, Q of mu n plus ZP k naught minus 1 tensor lambda n of H1 of Q of mu n plus ZP of 1 minus k naught. And so you can consider Dn the submodule generated by the x phi. When phi runs in this. No. So I'm going to explain another way to construct this X phi, maybe which is more down to earth. So if you look at Tn hat, so you can embed it in a product An cross Bn. So An is going to be the product of all irreducible components specializing to Eisenstein points, and Bn are the other ones. And you can consider eta n to be the annihilator inside Tno hat of Bn. So now if you take a phi tilde inside here, and if you look at x at phi tilde x of sigma tau, so if you look at this modulo W, then this element is going to be equal to 0 because modulo W also this element here is going to belong to An cross 0 because you have multiplied by something which is in the annihilator of Bn. So this element is going to be 0 modulo W because all the components here are restricted to Eisenstein points. So what you do is that you look at phi tilde of x sigma tau, and so you divide by W, and you can check then that this belongs to O delta n. And how do you do that? You use a trace map that I have explained before to check this. Because if you have an element in this annihilator, and you apply the trace of this element, it has to be itself. So, and you look at this element and you look at it modulo W. Then I'm claiming that this element is equal to the x phi tilde of naught that I have constructed before, where phi tilde of naught is the image of phi tilde by the map. Well, An lambda n, which is so that's another way to construct this element.
In the first instruction, suppose that the chemical Eisenstein points are etal over the white space.
Yes, I told that before.
Oh, you said that.
Yes, yes. But actually, we can get rid of this condition if we if the level goes to infinity, the p level goes to infinity, we can get rid of this. And the reason is that, so this is in the work of Bellet and Chenevier, is that if you have a point which is a critical Eisenstein point, the map on white space is going to be etal if only if the value of the periodical function at k0 minus 1, the character chi, is non-zero. But if you let the level go to infinity, then what you have is just a periodical function. We know it's always non-zero. So using this kind of ID, one can show actually that this module, when you let n, you replace n by, let's say, np infinity, then we can show that this module is torsion over lambda np infinity. And so we get element in lambda np infinity. So we can define, as I said, inconditionally elements in dnp infinity, which is included in H1 Q of, well, take the projective limit for R of H1 Q of NPR, NPR. So then we have several questions. So the first question is, how does it behave with respect to co-restriction? Respect co-restriction. And to see that, one has to remark the following, is that if you look at this map, take the co-restriction map, so we, as I said, this is isomorphic to H1, yeah, there is a plus, of Q lambda n k naught minus 1. So k lambda at L of k naught minus 1. Q lambda n k naught minus 1. So this map is just the canonical map from lambda NL to lambda n. So to check, to know how this behaves with respect to co-restriction, what we have to understand, we need to understand what is the image by pi NL is the map from lambda NL to lambda n. We have to understand the image of lambda NL not inside. And the claim so I'm not going to state it as a theorem because I haven't checked all details yet, but the claim is that pi NL of NL must be equal to, so 1 minus L k naught minus 2 diamond L, so n times 1 minus L minus k naught diamond L and inverse n. And so if you believe that, then that tells you that DNL, so take the co-restriction of DNL, you get, well, dn times the same factor here. And that tells you that if you take this family of elements, they behave as, well, if you have another system for k naught minus 1, Cn k naught minus 1, and you tensor it with the Euler system for Cn of 1 minus k naught. So the second question is that if we look at, excuse me, I forgot to put a k naught in the notation because this depends on k naught. If you look at dn p infinity k naught, take this is a projective limit of the dn pr k naught. So is this independent of k naught? So this makes sense to ask this question because when you look at the projective limit of h1 q of mu n p infinity plus of zp of k naught minus 1. So this module, this is going to be a lambda p infinity module. this module for different k0 you have a twisting isomorphism between this module for k0 and this module for another k prime naught. And so here independent means that if you look at this twisting isomorphism, do they correspond by it? And so the answer of this is yes. And this follows from the fact that the equal algebra I have defined before, when you go to the infinity, to p infinity level, they are independent of k0. That looks a bit surprising because one started with critical Eisenstein series of a given slope. And but, well, still. And the last remark I want to make is for this point, if we replace lambda n naught by eta n naught by eta n, it's going to be the annihilator inside now Tn k naught of lambda of Bn k naught. So what is Bn k naught? So you can embed Tn k naught in lambda n cross Bn k naught. So the map on this factor is the Eisenstein map, and the map on the other factor is all the other components. So therefore, this is just the critical Eisenstein. Well, I should put a k naught. Critical Eisenstein ideal. So, of course, we have an inclusion like this, and this relation can be verified much easier for this guy than for this one. Okay, so a remark that it's much more difficult to deal with Eisenstein series than with curved form, and therefore, if we consider all this strategy where you replace Eisenstein series by CM forms, then you can get a result by constructing Euler system, anticyclotomic Euler system. So you take Eisenstein series by CM forms. So you get anticyclotomic Euler system. And this is something also I am working on. Okay, I'm going to stop. I'm sorry for being late.